Welcome to the introductory video about electromagnetic waves or electromagnetic radiation, whichever wording you would like to use. This is chapter 34 in our book, and we're going to talk about it in class next time. So here is some information. The first section and the introduction go through what is called the spectrum, the electromagnetic spectrum. And then when you read in sections 2 and 3 about what are electromagnetic waves, and then you go on to 5 talking about creating electromagnetic waves and antennas, and then we'll talk about what happens to this radiation, these waves, with distance, and then on to something that is how a couple of very interesting topics, I think, the most interesting of these, which is how these electromagnetic waves travel through matter. We'll use glass as our example. And then on to what's called polarization, which is very, very interesting. And then the last section in your reading, section 23, is interesting in that it explains how polarization is used to create liquid crystal displays for your calculator and other parts. So let's start with the electromagnetic spectrum. The electromagnetic spectrum is a description of the names that we have given to different frequencies and wavelengths of these electromagnetic waves. A small portion of these, as you can see here indicated in the center here, are what are known as visible light, and the only thing that makes those special is the cells in the back of our eyes react to this type of electromagnetic wave within these parameters. We use things like X-rays and microwaves, which are in these ranges all the time. You know, our radio waves down here on the right-hand side, radar. I like this chart because it shows more realistically how the spectrum is broken up. But the second chart here, while it's not as colorful, I think gives a little more insight into why do we use certain electromagnetic waves for certain tasks. If we look, radio waves have a wavelength about 10 to the third or 1,000 meters, and their frequency is in hertz is about 10 to the fourth. That's about the size of a building. This is why radio waves were chosen to transport information over long distances, because they many times just ignore hills, buildings, other things of that magnitude that are in the way that would block other waves. Microwaves, likely, in the same fashion, were chosen because of their relationship in size to vibrating the molecules within food and allowing it to warm up, not just food, but water. And if you remember back, some of the classes got to do the little demonstration on figuring out this wavelength, this frequency. We get into infrared, and that is kind of the low end of the idea of visible. There are some animals that can see in infrared where we can't. Then you get into the visible range here, where notice it's about the size of a protozoa, this wavelength. And then you get down into ultraviolet, which is molecules, and X-ray, which is the size of atoms, and gamma rays, which are the size of atomic nuclei. And that is why these interact with the ultraviolet with molecules in our skin, X-rays with showing us how they're absorbed in our body and letting us see something, and gamma rays why they generally can interact with atomic nuclei. So the spectrum is very broad, and we use them for a lot of different things and a lot of different ways that we see them. But what exactly are electromagnetic waves? Well, electromagnetic waves are caused by an oscillating charge, and they create not only an electric field, but a magnetic field. Now, we didn't get a chance to really look at magnetic fields. When you have a changing electric field, That changing field, not just a field, but a changing electric field, causes a changing magnetic field, and they are perpendicular to each other. We could look at this as it comes down here. Now they have the magnetic field, the B field label as H, and that has to do with just how it's done in different countries. But it's normally called the B field. As this wave moves, the two waves, the electric wave, which is E and blue, and the magnetic wave, which is B, or in this case H in red, are always perpendicular to each other. Another way to see this is here, and I can rotate this around. So here we have our electric field in red and our magnetic field in blue, and they are always going to stay perpendicular as that wave moves. And this is the reason that these can propagate or move through a vacuum, is that, and they create, in my mind, they create their own medium as they move. Because if you have the electric field, it creates the magnetic field. The magnetic field creates the electric field. They're self-sustaining. And this is why they can move through a vacuum or a null space without being changed or affected. They do not need a medium like a sound wave does. Here is a video clip from Paul Hewitt explaining this further.
If you shake the tip of a stick in a puddle of water, you'll create waves. In a similar way, if you shake an electrically charged stick in the air, you'll also create waves, electromagnetic waves. Recall from a study of electromagnetism that a change in an electric field induces a magnetic field, and a change in a magnetic field induces an electric field, whereupon these changes and fields regenerate to form an electromagnetic wave. Electromagnetic waves traveling through free space never change speed. Why? The answer involves energy conservation. If life in free space were to slow down, its changing electric field would generate a weaker magnetic field, which in turn would generate a weaker electric field, and so on until the wave dies out. Energy would be lost and none would be transported from one place to another. In free space, there's nothing to accept this energy. Is energy destroyed? That's a no-no, so light cannot travel slower than it does. If light were faster, the changing electric field would generate a stronger magnetic field, which in turn would generate a stronger electric field, and so on, a crescendo of ever-increasing field strength and ever-increasing energy. Again, clearly a conservation of energy no-no. At only one speed do the fields mutually induce each other indefinitely, carrying energy forward without loss or gain. In 1865, the British scientist James Clerk Maxwell, using only the knowledge of electric and magnetic fields that had been gained in laboratory experiments, calculated that these fields should be able to propagate through space at 300,000 kilometers per second. He had calculated, he was surprised to learn, the speed of light. In a vacuum, all electromagnetic waves move at the same speed and differ from one another in their frequency and wavelength. Their classification according to frequency is the electromagnetic spectrum.
All right, we're back, and I wanted to look at this simulation here, which is we have a radio station over here on the left-hand side with its large antenna, and a house over here with its smaller antenna. And if we allow this electron to move, to oscillate, it creates an electromagnetic wave. Right now I'm showing the field. I could also show the force on the electron. You notice how that lines up with the magnitude of the wave. As that wave spreads out from that antenna, it loses some of it, but it's that oscillating electron that creates that field, which creates the electromagnetic wave that goes out to the house. This is looking at it as a wave. If we wanted to look at it as the field that it creates, here is the here is the electric field that moving electron is creating. Because remember, it's charged, so it's creating a field. And you can see that field is propagating out, radiating out from that electron, and that's what's causing the other electron to move. I'm going to stop it for a second, and you can see that wave is still traveling there. It moves at that constant rate. And now if we oscillate that, it starts creating that field spreading out from it. But we do have, as it spreads, we have that lessening of it. If we look at our equation sheet, this is very similar to sound. Notice that the intensity here that we had for sound was the power over this area, this surface area of a sphere. That's the same equation we're going to use here for intensity as it spreads out. Later, when we talk about polarizers, the only equation we use with polarizers is right down here. The intensity after an analyzer is the intensity after the first polarizer multiplied by the cosine of the angle between them squared. So these are really, for this, the only equations we have. The intensity reduces like it does with sound, and then we have the intensity due to the polarizers and how it goes through distance. Alright, the next section that I would like to talk about is how electromagnetic waves travel through matter. And we're going to go back to Mr. Hewitt, and he has a great explanation of this, and here's that video.
We call the speed of light in free space c. Easy to remember because it's constant. But in transparent materials, light travels at speeds less than c. To understand this, let's first look at a model of electrons about an atomic nucleus. The electrons of atoms have certain natural frequencies of vibration. It's as if they were connected to the atomic nucleus by springs. Atoms have a springiness to them. When light is transmitted through matter, some of the electrons in the matter are forced into vibration. In this way, vibrations in the emitter are transmitted to vibrations in the receiver. This is similar to the way sound is transmitted. When the tuning fork on the right has a natural frequency that matches the frequency of the incoming sound, it is set into vibration. And these vibrations can transfer to other forks not shown here. In a similar but not identical way, light passes through glass and other transparent materials. One of the things that bothered me when I first became interested in physics was how light, when slowing down in a transparent medium, speeds back up when it emerges into the air. If you fire a BB into a slab of balsa wood, it slows inside the wood, but doesn't speed back up when it emerges from the other side. So why should light? Aha, the answer has to do with this mechanical analogy. When you drop one or more balls against the array of balls, the ones to emerge on the other side are different balls. Likewise with light. Light travels in little bundles of energy called photons. The photons that first encounter a piece of glass are not the same photons to emerge on the other side. Here we see three of many atoms. In A, a photon encounters an atom on the edge of the glass. In B, it sets electrons in the atom vibrating. Guess at what frequency? That's right, the same frequency as the incoming photon. So what occurs in the atom's vibrating electron? That's right, in C, it emits a photon that is just like the incoming photon. The process repeats in cascade fashion throughout the glass. So at the far edge, the photon that emerges from the glass is just like the photon that started the process. Wait a minute. Light travels slower in glass than in air? Haven't we learned that light travels at a constant speed, c? Now here's an interesting point. A photon in free space has one speed c, which happens to be 300,000 kilometers per second, which is the speed of the photons in the free space between atoms. So we must distinguish between average speed of light and c. Because of a time delay between absorptions and re-emissions throughout the glass, light travels at an average speed less than c. Even in air, the average speed of light is slightly below the speed we call c. In glass, infrared waves with frequencies lower than those of visible light cause not only electrons, but the entire atoms of molecules to vibrate. This vibration increases the internal energy and the temperature of the structure, which is why infrared waves are often called heat waves. Glass is not transparent to ultraviolet light nor infrared light, but glass is transparent to visible light. I want to leave you with a question. First, notice that I use the sound of tuning forks in my explanation of light transferring energy from one place to another. Some people still confuse sound and light. So before we progress further into light, here's my question. What is the fundamental difference between a sound wave and a light wave? In their natures and in the speeds at which they travel? Until next time, good energy.
All right, we're back, and that is, I think, a really cool and really interesting explanation, because I never understood when I was in high school how the light moved through there, but then emerged at the same velocity it was going before. So the topic that we're moving on to now is polarization. Polarizers affect the intensity of the light by only allowing certain light through. I found this really great explanation video here that has a Slinky, and I think does a great job showing it and explaining it. So here you go.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
All right, so we're back. One other thing I want to talk about with polarizers is the main place that you will see them and you will live them in your everyday life is twofold. One is polarized sunglasses, and light is polarized when it reflects off the surface. And we'll talk about that more with reflection. And we call that reflecting off the surface glare. If we're in the afternoon and we're looking out of the classroom windows, we can see great glare coming off of the windshields of the cars across the way. Well, sunglasses, polarized sunglasses, are designed to cut that glare. Here's a great example of it done by another physics teacher in his truck.
I'm sitting inside my car, And I've placed a few items up on the dashboard. Here's the bright sun glare off my dashboard on the windshield of my car. And now I'm going to take my sunglasses, and you'll see the improvement in vision when the polarized light is blocked by the polarized lenses. There we go. There's the glare. The glare is gone. And if I rotate the glasses this way, you can see the glare is back. Rotating it this way removes the glare, and that's my garage in front of us. You can see inside of it. And now this way, the glare is back.
Alright, the other place that you would see polarization is in the creation of 3D movies. And if you're interested in that, answer the following question, and then we can talk about it further in class. So this has been the introduction to electromagnetic waves and electromagnetic radiation. I look forward to seeing you in class.